nanoHUB-U, online instruction.
Welcome back to Unit 2 of our course. This is the 9th lecture. Now, when we discussed these NEGF equations, I mentioned that there are these sigmas related to the physical contacts, but there's also a sigma, the sigma 0. That's not a physical contact, but it's about the interactions. And in this lecture, that's what I want to talk about. Now, irrespective of the origin of the sigmas, we had set up this picture that tells you the inflow and the outflow that's associated with various sigmas, because basically each sigma kind of represents, there's a sigma which represents the outflow and the sigma in which represents inflow. The difference though is that when it's a physical contact, then the inflow can be related to the outflow through this Fermi function. But this is a relation that does not apply to the interaction contact or the dephasing contact. At this dephasing contact, when the sigma 0 and sigma 0 in don't have any necessary connection that you could write down in terms of any Fermi function, because it doesn't have a Fermi function. But there's one requirement it must satisfy, and that is that the inflow and the outflow must be balanced. Because you see, at a physical contact, they are not equal, because there you could have a net flow of 100 electrons per second. So you could have 1000 coming in, 900 leaving, with a net flow in of 100. That's fine. But this contact, you see, there is no physical contact to collect electrons. So if 1000 are coming in, 1000 must be leaving just as well. Otherwise, you wouldn't have a steady state situation. Which means that when you write down this sigma 0 and sigma 0 in, they ought to satisfy this relation, namely that the inflow is equal to the outflow. So let me go through examples of how you could choose various kinds of sigmas so that this relation would be satisfied. So one example would be the following, that supposing we use a sigma 0 that is equal to a number times the retarded Green's function. Okay? So this is a matrix, that's a matrix, this is a number. And correspondingly, we choose the sigma in as d0 times this number matrix that Gn that we have defined. Again, we use the same d0 in both places. Right? Now, of course, because I have introduced this relation, when I try to calculate the Green's function, it will actually require a iterative process. Why? Because the Green's function depends on sigma 0, and the sigma 0 in turn depends on the Green's function. So I have to solve the two kind of self-consistently. And the same here. Gn depends on sigma 0 in, but the sigma 0 in depends on Gn. So again, you have to solve them self-consistently. But the point I want to show is that as long as you solve them correctly, this basic relationship would be automatically satisfied, and so current would be conserved. You would not be losing current into this dephasing contact, which is of course the basic requirement, because if that happens, you don't even have a consistent theory to work with. Now to see that, note that if sigma 0 is d0 gr, then the corresponding gamma, which is what I need here, that gamma 0 is I sigma 0 minus sigma 0 dagger, which is d0 I gr minus gr dagger, which is Ga. And the point is that quantity is A. So gamma 0 is d0 times A. So if you want trace of gamma 0 Gn, the gamma 0 is d0 times A, so it becomes d0 times trace of Agn. Here, sigma 0 in is d0 Gn, so when we look at the other quantity, sigma 0 in A, this one is d0 Gn, so when I put it in, I get d0 trace of Gn A. So you'll notice those are equal as long as I have used the same number here as here. Because this is trace of AGN, this is trace of GNA. And trace, as you know, you can reverse the matrices, move them around cyclically, and trace stays the same. So this is a choice that would conserve electrons. So it wouldn't give you loss of electrons into this contact. But physically, what does it lead to? What effect does it describe? Well, let's do this problem. We take this old problem we had, namely a wire with a barrier, which is kind of like a resistance, and you have the interface resistances. So as you know, if you look at the electrochemical potential or the occupation of the levels inside the channel, what you expect to see is it's 1 at this end, 0 at the other, and wherever there's a barrier, there's a drop in the occupation. This is something we discussed at length in Unit 3 of Part A. But basically, as I mentioned, that anytime there is a barrier, that's where the occupation drops. And semi-classically, you expect that if you think of the electrons as cars on a highway, a barrier is kind of like a construction zone. As soon as you cross it, suddenly the road is empty. So it's kind of similar. There's this drop here. So that's what you expect semi-classically if you're thinking of electrons as particles or like cars. But when you do the wave theory, you'd get these oscillations. This reflects these standing waves, interferences. That's what you'd get if you did a coherent quantum theory, coherent NEGF. But as I explained in the last lecture, it's important to include these random potentials, because that's what destroys this phase information. And what I claim is that this choice of sigma, namely sigma 0 equals d0 times the Green's function, sigma 0 n is d0 times the Gn, that includes phase relaxation. And indeed, if you do that and do the same calculation, what you find is the oscillations are subdued, kind of suppressed. And you get a quantum curve that almost looks like the semi-classical with a little oscillation right around that barrier. And this is the kind of thing people have seen. People can actually measure how this electrochemical potential varies around a defect, so on. And this is the kind of thing they have seen. Now, why does this work? How does it give rise to, how does it include this effect of random potentials? Well, you could think of it this way, that you see, you have E psi equals H psi inside your channel, and now you have a random potential which adds to the H, kind of like a UR times psi. And let us say we treat that UR times psi as a source term, as if this UR times psi is what kind of goes out somewhere and then comes back in again as a S. Remember, S was what came in from the contacts. So let's say we write the S as UR times psi. Then we could write SS dagger as UR psi, psi dagger UR. And SS dagger is what you call sigma 0. That's what we have been doing. SS dagger is like the sigma. Psi dagger is like Gn. And then you can see you have this relation. Sigma 0 n is d0 Gn. And what is d0? It is basically then the kind of the RMS value of this random potential. Note that this d0 has the units of energy squared. That's because sigma is like H. It is energy. It's electron volts. On the other hand, the G is the number per unit energy. So it's like per electron volt. And so this constant in between has the units of electron volt squared. And what it really represents is kind of this RMS value of the random potential that we have. And of course, in this model, the assumption is this is a number. So this potential is assumed to be the same everywhere. So it's like this entire thing has a certain random potential, but not like there is any difference between the potential here and there and so on. And that is why, I guess, because it's like a uniform potential, it actually doesn't lead to any loss of momentum. Notice that the entire drop is still here. There is no drop here. As in this region, there's phase relaxation, but no momentum relaxation. Because if there were momentum relaxation, there would also be a drop in the potential. And after this, I'll show you an example where there is a drop in the potential. But for this choice of sigmas, there is no drop in the potential. What you get is pure phase relaxation without momentum relaxation. Now, what I'm told is that people who do large-scale numerical computation, they don't like this one very much because you have to keep the entire matrix. They would rather have models where you need only the diagonal elements of the matrix. And I'll show you a choice after this where you do just that, actually. That is, you only keep the diagonal elements of GR when you construct the sigma 0, and similarly the diagonal elements. And so in a practical sense, of course, that saves you memory because you don't have to remember the entire, say, 1000 by 1000 matrix, just the 1000 diagonal elements. But in terms of the physics, though, while this method gives you pure phase relaxation, the other one gives you momentum relaxation as well. And let me show you with an example. So in general, then, the point I want to make is, previously I wrote sigma 0 is a number times GR. You could do something more sophisticated where you say, okay, I'll look at the ij element of sigma 0 and relate it to the ij element of GR and multiply it by dij. So in other words, previously we were taking the entire matrix and multiplying by a single number. Now we are taking the entire matrix and multiplying, each element by a separate number, dij. And we use the same matrix here, sigma 0 in dij times gn. And the point is that as long as the D matrix is symmetric, that dij equals dji, what I'll show is you'd still have a consistent theory because the trace of the sigma in A will be equal to trace of gamma gn, which means inflow and outflow will be balanced and you won't be losing electrons. That's always a zero-order check to make, because if you're losing electrons, you won't have a consistent theory. Well, the way it goes is, again, sigma 0 is dgr, so gamma 0 is dij, aij. You could work that out. And so trace of gamma 0 gn would be like, I guess, gamma 0 gn. I mean, when you write trace, what you're supposed to do is take the ij element of this multiplied by the ji element of that and sum over all I and j. Because trace means you're looking at the diagonal elements. So then instead of gamma 0, you put in d times a. So you get something like this. Sum over ij, dij, a, and then gn. You could do the same here. When you take sigma 0 in times a, again, you need the trace. So that's like sigma 0 in ji, aij, sum over I and j. And then if you put in the dgn, you'll get that. And the two will be the same as long as D is symmetric matrix. Okay. So in general, you could use any D. Now what I'll show you is one where we use a D for which has non-zero elements only on the diagonal. And we'll see, that is, where the D looks something like this. Some number, and then you have ones on the diagonal. Rest are all zeros. Whereas what we used previously was D was like the same for every element, single D0. That's what we used, and when we used that, we saw what we got, namely pure phase relaxation. And so you got a curve that looks almost like semi-classical. Well, when we use this one, what we get is, again, the oscillations have gone down, but now you see there's a big slope here. And these slopes, again, reflect this momentum relaxation in addition to the phase relaxation. And what is this D matrix? Well, it is basically then the average value of the potential at location I and the potential at location J. And previously we were assuming that it was basically the same potential everywhere, which is why all these elements were 1. Now we are assuming that the potential at any point is totally uncorrelated with the potential at the next point and with the next point, which is why any off-diagonal element is 0. Of course, the diagonal is 1 because it is correlated with the potential right there. It's the same thing. But there's no correlation from one point to another. And that kind of potential would destroy momentum because the potential is changing rapidly, will cause strong reflections. Whereas here the potential is almost constant, doesn't cause any reflections, no loss of momentum. And the effect is very evident when you look at the potential profile in your channel. So to sum up then, here, what we tried to do in this lecture is that talk about this dephasing contact, because so far we have been talking largely about the physical contacts. And at the dephasing contact, the key relation to keep in mind is however you choose your sigmas, this relation should be satisfied to make sure electrons are conserved. And this would be satisfied if you choose it in this way, according to this prescription, with the same D both places, as long as it's a symmetric matrix. So any symmetric matrix would work. And what I showed you was two examples. One where it was a full matrix, all ones, and the other where it was a purely diagonal matrix, which gives rise to momentum relaxation, while the all ones gives rise to phase relaxation. And in general, you could have more sophisticated choices also, where you actually have a tensor D with 4 indices, etc. You see, usually the way you get these Ds, the approach is you start from a microscopic theory. You say that, well, we are talking about phonon interaction, and phonons give rise to a potential like this, and this is the correlation of that potential. That's the usual approach. The approach we are taking is, well, we won't worry about the microscopic theory of where the potential comes from, but we'll say, what are, I guess, acceptable choices for D so that you don't lose particles? And then, for a particular choice of D, what does it relax? Does it relax phase? Does it relax momentum? Both? Or if you're talking spin transport, you might want to come up with a D that relaxes spin. And the attitude one could take is, we know the momentum relaxation time or the phase relaxation time or the spin relaxation time from experiment. And so we'll adjust our D appropriately to give us the right relaxation times. And then go on to analyze devices. As opposed to saying that we'll have to get the D from a microscopic theory of all the detailed scattering processes. What we are doing is, we are saying we are not going into that, instead treating the D as something you get from known experiments. Thank you, and in the next lecture we'll, I guess, sum up this unit.